Hi and welcome to the Allplane Podcast, where we talk with the movers and shakers that are redefining the future of commercial aviation. As usual, before we start, let me remind you once more that all previous episodes of this podcast, as well as many other aviation stories, are available on the Allplane website. That's Allplane.tv, Allplane.tv. Our guest today, Tom Grundy, is leading a project that is totally unique in the world of aviation. It is in fact unique in more than one way. First, because the company that Tom leads, which is called Hybrid Air Vehicles, is building what, by some measures, is the largest aircraft in the world. But also because it involves the comeback at the scale of a type of aircraft that marked an epoch right when commercial aviation was getting started about 100 years ago. In fact, as Tom will explain in this episode, the Airlander, such as the name Hybrid Air Vehicles has given to this type of aircraft, differs in some important ways from the classical airships. After all, Hybrid Air Vehicles benefits from almost a century of advances in aerospace technology and material science. The Airlander will come in passenger and cargo versions and will provide an enormous flexibility to its operators, since it doesn't really need an airport to take off and land, and has an endurance that is measured in days. Tom anticipates a market for hundreds of Airlanders, with one customer already confirmed, a Spanish airline called Air Nostrum, and his team has even started work on an even larger version that will be able to carry a payload of up to 50 tons, or the equivalent of 6 ISO containers. Tom expects the Airlanders to be a true game changer for logistics in many parts of the world, but it is best if we hear it all direct from Tom. Hi Tom, how are you?
Hi Miguel, I'm very well. How are you doing?
Very well. Where are you joining us from today?
So I'm joining you from here at the headquarters of Hybrid Air Vehicles Limited in Bedford, UK.
Excellent. So first of all, before we start talking in depth about this very exciting project, which is nothing less than the comeback of the airship, a very iconic type of air transportation. In a few words, a little bit more about yourself and how you ended up leading this project.
Oh, I joined the company here 10 years ago now. So I'm an engineer. I'm an aerospace engineer. I came out of BAE Systems. I came out of Airbus. And I found that I'd always been searching out the projects that were trying to do things differently, trying to get aircraft to places that was hard to get airplanes to, whether that was developing UAVs for surveillance, for those difficult surveillance missions, or taking a lot of cost out of the operation of fleets so we can make fleets of aircraft go further. And that search for efficiency and that search for getting aircraft to places where they don't usually go really meant that what the team were doing here with Airlander resonated with me. And so I joined in 2010 as operations director, took the operations of the company through the development of the prototype airplane and became chief executive in 2019.
A very, very unique project. We're going to kind of dissect it now a little bit. Something that it's very newsworthy, I think, because it's been how long? Like 7-8 decades since the last time that airships were a thing in aviation. There's been a few blimps, some air balloons, there's been some around, but not in a industrial way as you are trying to do now with hybrid air vehicles. So how this project came to be? I think the origins are in a military research project in the US, right? Then after some years, it became a British company. And I think you have already been flying some prototypes and you are pretty close to releasing a commercial airship. Can you tell us a bit more about this project, how it started and how it evolved over time these last few years?
Yeah, I can. This project's always been about two core things, really. It's been about doing things differently with the technology. Moving on from airships and moving the technology base forward and the platform and the configuration forward, and to really put a platform properly in the big space that exists between fast air transport today and slower surface transport options. So it's been designed to do a different job and do it in a different way with a technology base that's moved a long way forward from those of the past. And the second thing it's been about is doing it at scale. It's been about commercializing and moving this part of the industry to a point where it's delivering in much the same way that you see in the rest of the transportation and logistics world at scale, with products going into the market fully supported and operating in a way that all kinds of customers can engage with. And that's really been the guiding force for how the technology base was developed, how the company's been thought about. And then, of course, the third thing that's come out of that is by pursuing those goals, we have designed the world's most efficient large aircraft. So we can now deliver low emissions flight and highly economical flight at a scale that the rest of industry will take a little bit of a while to catch up with, certainly on the aviation side. So new technology, commercializing that technology and using that to deliver highly efficient air services in a different way.
I'm assuming here that most of the people listening to this are already familiar, or at least have seen some images of the Airlander, of the airship that your company is designing, or at least they are familiar with the concept of an airship. But just in case, because it's kind of a unique aircraft, let's just recap what it's all about. It's a large, very large balloon. I think it's actually the largest flying object in the world right now, or by some measures, I think by length.
By some measures,
right?
Indeed, yeah.
Yeah, it's actually two twin balloons, right, that are joined together with a rigid gondola underneath. That is where all the cargo and passengers and cockpit are located, right?
Yes.
And this is powered by a propeller and an engine that might be powered by sustainable aviation fuel.
So a mixture, actually. So what we have with Airlander is effectively a twin-hulled airship. And the reason we call it a hybrid, and the reason it is a hybrid, is it does some things in a very different way to an airship. So you think about those classic airships of old, they float. The obvious thing about them, they're hugely efficient, they float. So when they're in the air, they are very, very low fuel burn, very, very low emissions, very economical to operate. But the floating becomes a problem at the end of the mission because we need to unload payload. We need to put passengers on board. We need to fuel the aircraft. And so all the things that the rest of the aviation world take for granted become, in terms of quick turnaround, moving passengers on and off, getting the next flight airborne quickly enough to get asset utilization up. All those things become really hard. So with Airlander, this twin hull design is designed to give us enough lifting surface that we can generate 40% of the lift that the airplane needs from aerodynamic lift. So only 60% of our lift comes from helium in the way that airships generate lift. 40% comes from aerodynamics.
If I can stop you here 1 second, what does it mean in practice? This helps propel the aircraft, but in which way? So
that means that when the airplane stops, when we stop our engines, this aircraft comes down and lands on the ground. And it's as fundamental as that. An airship, if you stop the propellers, the airship's still going to float. With Airlander, you stop the propellers, they stop the engines, the aircraft comes down and lands on the ground. It doesn't have to be at an airport, of course. It can land in austere places away from today's infrastructure. But the point is, it's on the ground. So now we can load people, we can load shipping containers, we can refuel it, we can do all the things that you need to do to an airplane on the ground to turn it around for its next flight and make it an economically viable proposition. So for us, a hybrid aircraft, the technology we have here, it's a different category, it's a new thing. It is a bit like an airship, but it doesn't flow like an airship. It's a bit like an airplane, but it's far more efficient in terms of energy use than an airplane. And in terms of propulsion, which you asked about, yes, it's fitted with 4 engines. There are options there. So as a prototype, we flew it with 4 internal combustion engines. So burning jet fuel, but in a combustion cycle with a propeller, 4 propellers. And in that configuration, we have an aeroplane that will only use 1/4 the amount of fuel of any other equivalent aircraft for the jobs that it does. So 1/4 the emissions, even when using kerosene.
When you say an equivalent aircraft, you mean by payload?
So I mean by, if you look at it on a ton-kilometer basis or a passenger revenue kilometer basis, you're with all kerosene configuration, you're already at a 75% emissions reduction, 75% less fuel used per ton kilometer. And that's against a range of comparators and a range of modeled real world conditions. So it's a valid like-for-like comparison for moving people and things around the world. And then moving forward, of course, we've got that very efficient start point into which we can integrate the best of what's coming out of the aerospace world in terms of hydrogen fuel cells, hydrogen storage, and electric motors. So we can integrate, and we'll integrate electric powertrain as we go forward. So when we look at first operations in service with airlines, we're expecting those operations to be with the engines in a hybrid configuration, 2 electric engines being designed and developed at the moment by Collins Aerospace with the University of Nottingham. That's an ATI grant-funded program delivering those, teamed with hydrogen fuel cells, onboard hydrogen storage, and 2 combustion engines left for range extension in just the same way your hybrid car has got both options together at this point, until fuel cell technology matures to the point that we can get the full operational ranges from an all-electric variant. So that's both where we're starting from and where we're progressing to.
Interesting. So a very, very flexible platform for all sorts of technologies that now are being developed with the aim of being more sustainable, which is a big debate now, which technology is going to ultimately prevail.
Yes, it is big and flexible, both from a point of view of the use cases of the aircraft, which I'm sure we'll talk about, but just thinking about that technology integration opportunity that we have here with Airlander, you've got a different trade space to play with. So we've got a lot more space, a lot more volume available, not just for passengers and cargo, but also actually things like hydrogen storage. So we watch the way that the path to hydrogen aviation is developing out, both through the work that's been done here in the UK, and also Airbus and others around the world. And obviously there's a fairly strong move there towards hydrogen and towards liquid hydrogen. And we're both tracking that and looking at the opportunities that we have here with more volume on board to play into that space a little bit earlier, and with less installed power requirement to pull forward some of the powertrain technology and take it further quicker.
To the untrained eye, or let's say like someone that is not an expert like me in this type of technology, it might seem that a big part of the efficiency comes from the ease with which these, maybe it's not the right word, like you said, like classic airships float. Yours doesn't really float. I don't know if that's the right word, but the ease with which it moves through the air because of this lightness of the double hull. But still, I would like to revisit this point because I'm trying to understand which sort of material is it made of and how this inflatable carcass is made. Because when the engine stops, it goes down. But if it's filled with gas, I don't know which gas exactly is it. It's going to be there. Helium. Shouldn't it have some lifting power in the sense that it would remain airborne, even if it doesn't have propulsion? What are the principles at play here that make it go down compared to the previous generation of?
Okay, yeah, I understand. Yes, so if you think about, if we think about an original airship, you've got a cylinder that's filled with a lifting gas.
Yeah.
And you put enough lifting gas in that hull can lift itself and its structural weight and its payload and all the fuel it needs. And almost all of that lifting is done by the lifting gas inside. When you look at Airlander, we don't put enough lifting gas inside for the aircraft to take off. So there's just not enough. There's just about enough.
Okay.
So that when the aircraft's empty, it just sits on the ground with a little bit of net weight. Now we put our passengers, 10 tons worth of passengers or payload, and a fuel load on board. And now the aircraft is heavy. It can't lift without moving forward. So we now propel the aircraft forward through a rolling takeoff, short takeoff, bit of vectored thrust from the four motors. And that gives it the airspeed and the aerodynamic lift over that whole hull, over that whole gas-filled hull, acts as a lifting wing. That's what then gives you enough lift to take the fuel and the passengers or the payload weight up into the air. So
and how vertical is this lift? So it's on the ground, then it goes
so the
up?
Aircraft it'll take off in still wind conditions, it takes off in 6 times its own length. So that's about a 600-meter takeoff run in still wind. It's got a rotation speed that's very low compared to fixed wing aviation. So we'll rotate at somewhere between 20 and 25 knots. So it's a slow, it's a short takeoff with a rotation early, which you can do, of course, because so much of your lift is coming from the vertical lift vector of buoyancy.
Yeah.
And then to your point about efficiency, once you're in the air, Of course, your induced drag is much lower. Your skin drag is much lower because you're going because the aircraft's traveling slowly. You get all of that inherent efficiency from the structural mass being carried by the helium effectively for free. So we're getting a big head start against gravity. And the material science side of this, just very briefly, because it is a core part of our intellectual property that's allowed us to do this in a way that some years ago wasn't possible. We have that the aircraft hull is made of a very high spec, high tensile strength material. It's a 3-layer composite fabric, developed and proven out through our prototype flying, that allows us to generate this complex structure from a flexible fabric and have the shape and the rigidity and the strength that we need to carry the sorts of payloads that we're talking about in Airlander.
Okay, so the helium would still provide a decent amount of buoyancy.
It's a head start against gravity, a big one.
Yeah. Okay, then the landing and takeoff, where would that be? Because the classical airships, they had those masts that are basically like a pole that they attach themselves with a hook. I don't know if this is an option, considering what you just told me, but I guess it's way more flexible than a conventional aircraft in the number of places that it can land at.
Yes, it's designed to operate from any reasonably flat surface. That can be grass, it can be tarmac, of course, but it doesn't need to be. It can be grass, it can be marsh, it can be ice. Quite excitingly for us and for our customers, it can also be water. So, right back at the start of our conversation, said what we're doing here is putting a technology that sits in between what we currently do on the surface with things like ships and what we do at the moment with fast movers like aircraft, and opening up that ability for this aeroplane to operate from the waterfront, offers a huge amount of flexibility to our customer base for logistics and passenger connections in parts of the world that aren't well served by airport infrastructure right now. So yes, it's designed for those point-to-point operations. When it's on the ground, it obviously it's got its own weight, so it can sit on the ground and load and unload passengers or people. So think about it a bit like you might think about a helicopter operation, where sometimes a helicopter goes down, the passengers jump out while the blades are spinning. Sometimes the helicopter stops and is held on the ground and parked there overnight. For us, the overnight option is a very small, compact, mobile mooring mast that, when the aircraft's on the ground, sits in underneath the chin of the aeroplane. So if you can imagine those old airships moored right at the nose, right at the front. For us, it's a little bit different. We come right in underneath the front of the aeroplane, so it can be a low mast that's holding it there on the ground. And that system will keep the aircraft safely on the ground in up to about 80 knots of ground wind speed. So the aircraft's designed to then sit and operate and be maintained, refueled and everything else outside without needing to go into a hangar.
And if there was no mast available, the weight of the aircraft, where would it sit? It would be, does it have some wheels or some sort of platform to make contact with the ground?
Yeah, it sits on its own inbuilt inflatable skid, if you like, that sits underneath the airplane. So it's like our version of a landing gear. It deploys just in the way that a landing gear does. It looks very different. But that's what the aircraft physically sits on when it's on the ground on its own. And then, as I say, when you want to hold the aircraft, keep it there, you're in a maintenance period or between flights, that's when you connect it to the mast at the front to hold it in place there.
Does it need any type of ground support infrastructure? I guess in some cases like bases and stuff like that, there would need to be some minimal amount of ground support. But let's say it flies somewhere in the middle of nowhere. Does it need any ground equipment for the landing and liftoff, or it can just do it on its own?
It's designed for the widest set of use cases possible to get to parts of the world that are currently, as I say, not well served. So the answer to your question depends, like any other aircraft, on what you're doing with it. So if you're just going somewhere to drop off passengers or payload, then you can literally land in that clear flat space that you want to deliver the payload to, deliver that payload, and then take off again and go back out the other way. If you're coming back to the main base of operations for your operator, or if you're holding the aircraft somewhere between flights, you'll need that mobile mooring mast. But beyond that, the maintenance activities for that aeroplane can all be done outside, so no need for hangarage at the operating locations. It's just designed for the maximum amount of flexibility. And that's really important for us when we think about the use cases for Airlander, particularly in logistics, which we think is around about 60% of the forward market for aircraft of this type. So in those logistics roles, what we want to be doing is unlocking connections to parts of the world that are currently difficult to serve. So I'll give you an example. In Canada is a great example. There's communities of people and also industrial sites and mining sites that are very difficult at the moment to serve with equipment, with food, with logistics supplies, and equally difficult to get the produce out of those areas and back. So in those areas of the world, we're designing to be able to get efficiently cost-effective services into those communities and bring out the produce that those communities produce and get those into the rest of the logistics networks in mainland North America in that example. Another good example, on our Airlander 50 program, one of our development partners there is Blue Skies Holdings. They put a lot of the fresher fruit and vegetables on our shelves here in the UK. And for them, it's all about looking at how we can unlock wider parts of the producing areas of the world to get quick connections into the main markets for fruit and produce. And it's just those sort of opportunities and those sort of use cases that we're designing for. And obviously that flows through then into the way that we design the ground footprint, the operating footprint, the maintenance and turnaround of the airplane.
Yeah, Blue Sky Holdings, which are a producer of tropical fruit, I think, right?
Yes.
So I think that, that was started as an alternative to basically transfer tropical fruit out of West Africa, I think.
Exactly.
And put it into the global supply chain faster and more efficiently. I think another use case, I had a chance to write an article for CNN about a company in Sweden called Ocean Sky that was considering using vehicles like the one you're developing to do tours, luxury tours of the Arctic. So they told me one of the advantages was this ability to stop in places with no infrastructure. It could be in the middle of the ice in the Arctic, and also to go very slowly, to fly very slowly so that you can appreciate details on the ground that you wouldn't be able to see with a normal aircraft. It goes much faster.
Yeah. So here's some really interesting use case, and it really speaks to some of the advantages of this aircraft. And companies like Ocean Sky looking to use this sort of platform, exactly as you say, to be able to give a viewing experience and to be able to get to places that other aircraft can't get to, and to do it in a way that's economic and environmentally friendly. And some of the things that make the platform really strong there: low emissions, go anywhere, sit in a comfortable environment, a livable environment in a big cabin. That's, just to give you a feel for cabin size, that's a cabin that's longer than an Airbus A320 cabin. It's wider and it's got a more rectangular cross section, so you can stand up all the way across it. It's got floor to ceiling windows. In fact, we've put a few windows in the floor in that design, so you can see through to what you're going over. You're operating at 3,000 to 5,000 feet, probably typically in that sort of application. So you're in and amongst the scenery, you can see things going on around you. And it's quiet, it's vibration free, and because it's unpressurized in that cabin, you can even open the windows, right? So now take those attributes and put them into the aviation and transport world. And what we have is an aircraft that, same cabin, can be fitted out with 100 seats in roughly business class accommodation and run passenger services over relatively short distances, simply because journey times, airborne elements of journey times, are a little bit longer in Airlander because we're flying a little bit slower. So over the short distances, short sectors, sort of regional jet type distances, that's not a big time disadvantage. Added to which, getting on board and getting off board the aircraft, if you've got an off-airfield connection, can be much quicker. So equivalent journey times in this comfortable, spacious cabin for prices that are equivalent to today's transportation prices, and with only 10% the emissions at service entry and a path through to zero emissions flight by the end of the decade. It's that same combination of features that companies like Air, Ocean, Sky look at for expeditionary travel that have brought this into the attention of companies like Air Nostrum, who are leading out on the airline side with putting 100-seat versions of Airlander into those sort of operations and doing that economically and doing it quickly so they can make a big difference to the carbon footprint of their operations.
Yeah, indeed. That's actually one of the things I was about to mention now. Air Nostrum, Spanish regional airline that is operating as a franchise of Iberia in Spain and Europe and other countries in Europe in relatively short distances, like, for example, from the Spanish mainland to the Balearic Islands, this type of routes that could be relatively easily covered by an airship, and they could actually reach some points on those islands more efficiently than today's aircraft, because if you want to go to, I don't know, Mallorca, for example, you need to go through the main airport, which can be crowded in summer and all that. But I guess with the Airlander, you could just go to some locations that have traffic, for example, in summer, direct, and drop the people there.
Yeah.
And Air Nostrum is actually your launch customer. Am I right?
Air Nostrum's our launch airline. Yeah. So
Launch
they're
airline.
going to be, it's a landmark deal for us, and I think for them. It's a 10 aircraft reservation that they've made to put 100-seat Airlanders into that network. As I said, our company has been about rethinking the skies, producing something that does a different job in its own category in aviation, and doing it in a way that we scale up into commercial operations in the way that the airship world has never previously been able to do. And in the Air Nostrum work that we're doing, you see those things coming together. We're now into multi-aircraft orders for established airlines, for regional transport, 100 seats. And for us, that's absolutely been a key stepping stone for us as we build Airlander out into the market. And just to give you a feel for where I think that takes us, we're putting production capacity in place to deliver 24 aircraft a year into the market from 2027. My first aircraft in service type certified in 2026, and from 2027, we've got the capacity coming on stream to deliver 24 aircraft a year thereafter. So that's our base case, right? That's what we think the market forecasts conservatively support, and what we think, our interpretation of what the market is and the initial customers are saying to us right now. And that's really then a starting point that is substantial enough that it allows us to build out into bigger aeroplanes as we go. And why would we want to do that? Well, at Airlander 50 scale, you've got something that can carry 200 passengers or 50 tons of cargo, 6 shipping containers worth of cargo, and get that cargo into parts of the world that aren't well served. And critically, to do it at net zero. And what we're aiming for is to be doing that at actual zero emissions at that point. So as we look at, as I look at what's going on in aviation generally, there's naturally a very big focus on what the current single aisle fleet in particular, and of course the long haul fleet, wide body fleet as well, are doing, and what the emissions impact of that will be. But I also look at the growth vectors in aviation, with big growth in cargo, got big growth in markets that aren't so big, pent up demand in markets that aren't well served by aviation right now. And we need to unlock that growth and unlock that opportunity to deliver cargo, but we need to do that without making the emissions problem of aviation any worse. And when we do that, and we look at things like the current cargo markets and ask yourself the questions of, well, okay, if we were designing this from scratch for a net zero future, how much of air cargo actually needs to be moving around the world at 500 plus miles an hour, and how much actually would be just fine if it arrived in 24 hours rather than in 5 hours? Then we see there are huge opportunities across the network to make quick changes and quick wins in our battle for aviation to do its bit, more than its bit, and in response to climate change. So really, you've got these sort of 3 factors now. You've got the ability to unlock parts of the world and demand that isn't currently able to be well served by the economics of today's air transport. You've got the ability to provide additional services around congested areas and scale those quickly, because you don't need a lot of infrastructure with Airlander. And you've got the ability to do that without incrementing the emissions problem. at worst, without incrementing the emissions problem. And at best, you got a lot of opportunity actually to make some quick wins and bring down aviation's emissions in the markets that are tractable by a technology like ours.
Excellent. You are currently working on two different models of the Airlander. There's the Airlander 10, which is the one that Air Nostrum has in principle committed to. Then there is the Airlander 50, which is a larger version. Let me just review very quickly the specs of each of them so that people can get an idea. That's the info I got from your website. Correct me if there's been any change, but basically the Airlander 10, the one with a capacity for 100 passengers or 10 tons. I'm assuming it's either 10 tons of cargo or 100 passengers, yeah? It can fly for 4,000 miles, quite a distance, and has an endurance of, it can stay airborne for about 5 days. That's quite a long time. I'm assuming that's at minimal speed, just preserving fuel, or does it need to have some sort of special conditions to be able to stay airborne for such a long period?
No, it's designed to stay airborne for 5 days, in not in all conditions, but in a wide range of conditions. And that's principally for the surveillance applications of the platform. So we haven't talked so much about that, but there's a defense use case here, and also organizations like Coast Guards and Maritime Patrol, operations where long endurance gives you the ability to take big sensors and equipment and protect people, protect things on the ground or at sea.
Yeah, actually, you touch upon a topic that I wanted to ask you about, because as we briefly mentioned at the very beginning of this podcast, the Airlander actually started as a military defense project in the US.
That was certainly the big first commercial step. The founders of the company would say to you that they founded the company and they developed the technology to have multiple applications, just as we're developing here. But in 2010, the company was selected to deliver one of these aircraft into a US Army program for a surveillance mission. And that's really where the technology moved from being a subscale demonstrator up to being the full-scale aircraft that we flew, prototyped, and developed to reach our production standard.
How is it that then it went back, to say it in some way, to the commercial? So you refocus onto the commercial market rather than continuing being as a purely defense, well, not purely, but more of a defense-focused venture?
Well, it didn't quite feel like that for us as a business, because the job for us has always been to bring the technology forward through a path to market that allows it to be exploited in both commercial and defense applications. So where we've ended up is pretty much where we would have wanted to end up, which is with a product that is will be type certified, will carry that civil type cert. Our production line, those 24 aircraft a year, from our perspective, we're driving that production line to deliver a common Airlander 10 aircraft, whether that will go into a defense role or to commercial role, it'll be the same aircraft that comes off the production line. It'll then, of course, be fitted out differently for those two roles. And that allows us to drive a very efficient production line process with aircraft using the inherent space that we've got available on the aeroplane to provide a cost-effective customization and fit out then into commercial customers like Air Nostrum and defense customers like ultimately the US DoD and others. So that really, we would always have said to you through the whole time that the company's been developing the technology, that's really where we want to get to. 2010 to 2013, we had this opportunity to work with the US Department of Defense to take a defense version forward. And while that program was running, it did feel like that was very specifically a defense program, because of course it does when you're running a first of type in that way. And it's fair to say that the specification of aeroplane that dropped out of that, which became our prototype for Airlander 10, was more lent towards the military application, towards those long endurance. If people look at the history there, they were really pushing to get 3 whole weeks of endurance, which the average commercial customer doesn't really need to be in the air for 3 weeks at a time.
Yeah.
So between then and now, all that happened is that the operation that aircraft was originally intended to go into in the Afghanistan wars of the early part of the last decade, thankfully wound up. The aircraft became our property. We then were able to take it forward through the joint commercial and defence market specification process we've been through, to the point where now our order book, with $750 million worth of aircraft now reserved, is now ready for us to take that production aircraft into production, standard aircraft into production. And as it happens, the first aircraft coming into service will be commercial, and 60% of our forward market, we think, is on the civil side of the business, and 40% probably on the defence side. So that will come along as well. Then stepping beyond that, Airlander 10 is really designed with that 5 days endurance for defence applications, or 10 tons and 100 passengers. It's designed really mainly for the surveillance roles and the mobility, passenger mobility and transport roles, and the sort of tourism pieces that you see as well. For the logistics market, we want to be getting the efficiencies of scale that come with just being that little bit bigger. So you take the basic Airlander concept and scale it up. So a 90-meter long Airlander 10 becomes something like a 120-meter long Airlander 50. But with that increase in length, of course, you get a huge increase in volume and a huge increase in lifting capacity. And that moves you from Airlander 10 to Airlander 50, where we're now in 50 plus tons, 6 shipping containers, big logistics.
Or 200 passengers.
Or you could put that into a passenger operation with a much greater number of passengers,
And a hybrid configuration as well, from what I've seen on your website. There's a mixed cargo and passenger option.
So again, I think, again, there's all sorts of ways of managing that space within the aeroplane. And I think for large parts of the world, I think combination operations are going to be very interesting. There's lots of parts of the world that very difficult to get to for the people that work there or live there, but that difficulty comes with its own logistics challenges as well. So supplying them with food and supplying the and getting product back out again. There are a number of mixed mode cases, as you say, that I think are going to be quite powerful there.
The Airlander 50, it's going to have more payload, but slightly, like half the range, so 2,200 miles from what I read here on your site, and it's going to be even larger than the Airlander 10. So can we safely say that the Airlander 50 is going to be also like the largest aircraft in the world?
It'll certainly beat Airlander 10, but we have a lot of efficiencies playing out there. So of course, as you double the length of something, you're multiplying its volume by a factor of 8, right? So to move from 10 tons to 50 tons, it's not like we're having to make the airplane 5 times longer. So as I say, it's sort of going from 90 meters Airlander 10 to about 120 or so meters Airlander 50. That gets you there. And then the rest of the specification, including range, it's exactly where we are in that program right now, is working with our initial interested customers for that aircraft on the specification. So we've welcomed Blue Skies Holdings, we've got AECOM, one of the world's biggest infrastructure services firms, interested in how Airlander can unlock development projects that are currently costly or difficult to operate. We have Infinergy, who wind turbine blade transport interest there. Of course, Airlander's huge volume allows us to do things that other aircraft can't, things like wind turbine transport into remote parts of the world where we now obviously want energy producing infrastructure to be built out. And Highlands and Islands Airports Limited, of course, who their challenges are exactly as you've just described, passengers, but also the logistics questions of how you serve the scattered islands of the Scottish nation. So we're now working with those companies and others to refine that specification of Airlander 50 so that it will follow straight on after Airlander 10 and be in the market in the early years of the 2030s.
Because when it comes to certification, where does the Airlander fit? Is there a specific certification category, or is it going to go through the same process as a conventional airliner?
No, there is a category now. So we've worked with, a lot of this work was done with EASA, and also with other companies in the lighter than air space. So companies working on traditional lighter than air aircraft, airships. That work has developed the certification specification for this class of aircraft. That's been published by EASA. Of course, certification now for us as a British company will be run through the CAA, but with EASA and the FAA in parallel activity alongside with us. So that's been a big part of the work that we've done since flight testing the prototype. We learned a lot about the operation, a lot about the regulations that should apply, and that's allowed us to lay down that certification spec. Now, of course, underlying that are exactly the same certification and safety criteria as govern the rest of passenger aviation. So, the underlying logic is the same. The structure is slightly different because the aircraft type is new.
Yeah, indeed. And when it comes to the manufacturing, how you plan to do it? Because I'm assuming there is not really a ready supply chain like you have in conventional aircraft. You've got a whole range of new materials, technologies here that need to be put together. And you mentioned 24 aircraft per year, which is a pretty large aircraft. So are you planning to build a manufacturing facility in the UK, I guess? And how you plan to put together all this supply chain? Does it exist or you need to create it from scratch?
Yeah, so let's talk about supply chain first. So there's it's a new package, this Airlander. It's a new category of aircraft, a hybrid aeroplane. But the component parts, we can go into existing supply chains to deliver from. So if I just pick a couple of examples for you, the material and the hull assembly, we've worked with a company called ILC Dover out in the United States. They produce large fabric structures for all sorts of different applications, including components in NASA spacesuits, spacesuits for NASA, that sort of thing. But also big fabric assemblies. So we're going into supply chain that exists there. Engines, the combustion engines for Airlander 10 are from Red Engines in Germany. That's an existing unit, having been selected for integration with Airlander 10. We have got Collins Aerospace already developing the 500 kilowatt electric motors that will be the form the electric powertrain there. So, and I can carry on here. In each part of Airlander, you're really integrating either materials or systems that exist and are in use elsewhere into a new package. In terms of then when you come to assembly, that is different. So it's a very big aeroplane and it needs a big facility to put it together. Train
professionals as well. The professionals that will need to be trained to assemble this with specific skills and knowledge. I don't know how transferable are they from other industries.
So it's a very modular aircraft to build. So it's the best way to envisage it really is that the structure of the aeroplane, the thing that the effectively our primary structure is that fabric assembly. So you put the fabric together first. That's the biggest component, and then all of what we call the hard structure, whether that's the cabin, the gondola underneath, long composite module, or the individual engines, motors, or control surfaces, they all attach on the outside. So our production concept here is all about bringing those modular pieces in from the supply chain and then integrating them onto the hull in the final assembly facility. And in terms of the skill sets needed there, most of those are standard aerospace skill sets. There's one difference, which is there's not a lot of fabric, albeit, we've got what I really think of as a flexible composite material, which we casually call a fabric, but it's a 3-layer composite material that we use to give Airlander its external shape and its strength and rigidity. And those skills are a little bit different, but we've been through this twice through the prototyping program as we've built the aircraft and then taken it through several phases of flight test. Those are trainable skills from an aerospace skills base. So all of those pieces come together then in a big facility. We've teamed up here with and worked with partners in South Yorkshire. We're looking to put that production line in South Yorkshire near Doncaster. A number of reasons to select that, including the space, the access to skills, relevant skills and supply chain there.
I was guessing you need a very large place, I guess, because if you have all these aircraft simultaneously being built, those are pretty large. So you would need.
Yeah, you need a big area. But again, the technology that we're working with is fascinating because you can think about it in different ways. You know, we think about classic aerospace. I certainly think about classic aerospace facility when I think about building any aircraft, Airlander included. But you go into a shipbuilding facility, it looks very different. You look into places to build trains, it looks very different. And of course, the requirements that have been used to generate that production line are totally different in those applications. So here with Airlander, we've got a very lightweight structure. We've got a structure that you actually build the structural part of it in modules, put it together, and then it's got its own strength, its own integrity right from the start of the build process. So there's a very low requirement here for jigs, very small requirement for tools. There's very low floor loading at any point in the build cycle. The maximum lift, physical lift, crane or gantry lift is very light. So actually the structure that you need to put up around the bit of space that you're building on is relatively simple. And so with that, we can manage the cost base of that facility and scale up progressively through building production line slots around those aircraft as we go.
Yeah, sorry, I interrupted you earlier when you were finishing the reasons you selected that location in South Yorkshire near Doncaster. So it was the availability of space, availability of people.
Yeah,
professionals.
Also you talked about supply chain, and that's obviously key. So, and I think about supply chain actually not just at the front end of the life cycle here and in the build phase, but also we need a supply chain around aircraft operations. We need supply chain around training, maintenance, and so on. So we have teammates up there, including companies like 2XL Aviation, who, as I'm sure you know, have a fantastic range of commercial and defence services with a mixed fleet of aeroplanes, and really working with us on the operational side and the entry into service side of the Airlander project. And the Advanced Manufacturing Research Centre. So we've built a very strong relationship with the team up there at the AMRC. This will be the first time that a technology like this has entered rate production and scaled up in the way that we're looking to scale up. And so we're leveraging all of that skill and experience within the AMRC of their thinking about factories of the future and techniques, tools, and systems that allow us to scale this platform cost effectively. I think one of the things for us, and it comes back to the guiding light for us all really, this is about commercializing this product. It's about taking a product into the market that meets the price expectations of our customers. And so when we think about supply chains and locations and skills, we're really trying to marry the best of aerospace with the best of what we see in the rest of the transportation world, and develop a supply chain and a delivery system that is fit for an aeroplane that operates at, in passenger operations below 10,000 feet and at 70, 80 knots. It's a different set of facilities, a different set of skills, different set of supply chain components that you need to make that happen cost effectively.
What about the financials? I don't know if it's been published, but is there an official catalog price for a unit of Airlander?
There isn't an official published catalog price for one unit of Airlander. Yeah. But the way we've worked with this, it's about doing things that are suiting the technology that you've got and the unique aspects of that technology. So if you think about Airlander, it's big, right? So it's big as a physical item, and then it's very, very low energy use and very benign in its operational environment once it's in service. So our combination of fixed and variable costs with Airlander is quite different to what I'm used to in the fixed wing world. So slightly higher proportion of fixed cost, much lower proportion of variable cost. So what we look to maximize the advantage of that for our customers. It actually enables you to think about the value chain in a slightly different way. Who does what? Are we going to go with a traditional OEM handover to customer? Are we going to go with a traditional spares and repairs model? We're going to do something more integrated. And where we've ended up is working with partners to enable a mix of lease operations and procurement, direct procurement for customers. Whichever option those customers take, what they end up with is a product that in some roles, we'll take defense surveillance as one, the cost per unit of output, so a surveillance hour, the cost per surveillance hour there is going to be somewhere around about a factor of 10 lower than what we're used to paying for in fixed wing aircraft surveillance. In passenger operations, you don't quite get that same scale because it's shorter distance operations. Nevertheless, even today at 2021 fuel prices, 2021, so before the recent disruption in the fuel market, in the energy markets, the aircraft is lower cost to operate than an equivalent fleet of aircraft of the type that you do, typically regional jets on those sort of operations. So you start off with the cost advantage before we start thinking about future fuel prices and before we start thinking about the cost of carbon.
And I guess the same applies to cargo as well. Same you told me.
And exactly the same applies for cargo. So you're in this middle space with cargo where you're much cheaper than the aircraft flight, and you get cheaper and cheaper on a per ton kilometer basis as we scale up towards Airlander 50 and ultimately beyond. You're a little bit more expensive than surface transport of some types, particularly container shipping is obviously for long distances and extraordinarily efficient. But for anywhere where you're reliant on putting in a railway or operating a railway, or where you're dealing with comparisons against road transport, then Airlander operates in that middle space. Mm-hmm. It's a middle speed and middle price option between surface transport and air freight.
Yeah, sounds very, very interesting. Actually, it sounds so interesting that before wrapping up, I wanted to ask you, what's different this time? Because, well, there are obvious differences with the classic airships. About 100 years ago, airships were like the dominant, well, I don't know if dominant is the right word to say it, but they were pretty mainstream, or at least that it looked like it was going to be the future of air transportation. And then right by the time of the war, that was over. Really quickly, it kind of fell out of fashion. There was things like the Hindenburg incident, et cetera. And then after the war, the airships never really came back. So what is different this time, aside from the obvious differences that you mentioned compared to the traditional airships? What are the obstacles for this type of transportation not having been attempted earlier?
I have two answers for that.
Okay.
So the first is that we've set out to deliver a technology base that allows a new set of services to be delivered economically. So new technologies, fabrics, design methodologies, computational fluid dynamics, finite element models, all these things that weren't available back in the times that you were talking about, have allowed us to create a technology that we believed and are seeing opens up new applications that actually the aircraft world haven't been able to get into. So when you go back to logistics, 35% of the world, give or take, of the world's logistics by value goes by air, right? But it's only 1% of the volume of logistics going around the world. There's a lot of logistics that's still going by surface, and there's a great opportunity in the middle there to provide a premium for the material that can't currently get to market one way or the other by ships or by flight. So the start of this company was all about opening up those opportunities that actually air transport can't get into right now because it's not economical and we're not doing it. So there's underserved markets and a great opportunity there. And it's technology that's allowed us to do that. That's been the big obstacle, and that's what we've come over principally with our design of the hybrid, and all the technologies that you need to make that happen allows us to deliver an economic proposition to customers that an airship never could. It's a second answer, which I'd give you, which is that we've lived with abundant fossil fuels in aviation and everything else in the world for all that time since the Second World War. And those times of us being able to access kerosene at a price that everybody will complain about, but of course actually is, by the standards of the traveling passenger, delivering a very cost-effective service for that passenger. Well, we're seeing the change coming now, aren't we? We're not in that era of abundant available fossil fuel. So on top of all of the things that caused us to develop the technology and build the company and bring this to market, we've now got the imperative to move away from the source of fuel that's fueled aviation right from the start, And that's opening up a whole new space, and one that is critically important, and one that delivers huge opportunities for us to do things a little bit different, but in doing it, get a quick win under our belt in our fight against aviation's emissions.
And what about helium? Isn't there a shortage of helium in the world?
It's a finite resource, but there's plenty of it around. So the US Geological Survey has identified 50 years of known resources of helium at today's usage rates. And
in the US or globally?
No, in globally, although they like other sources, like other what's the word I'm looking for? Resources.
Yeah.
They extrapolate and say there's more than that out there that we've not found yet.
Mm-hmm.
But to give you a feel for that, it's 50 years there at today's usage rates. 600 Airlander aircraft of the Airlander 10s and Airlander 50s that we've talked about, they would account for less than 1% of the world's annual usage of helium.
Okay.
People do worry about supply side shortages because they do exist. We occasionally get a supply constriction because certainly if you go back 5 or 6 years ago, there were relatively few sources of helium coming onto the market. Any disruption to those meant that we weren't able to get party balloons and that sort of thing. So, we notice it. Mm-hmm. But actually industrial helium's always been available to us. There's 50 years worth of it out there and known worth of it out there. And for us, it doesn't become a big driver of operating costs. So we're relatively insensitive to the price of helium because you're not consuming it in a flight. The aim is to put the helium in once and leave it in there.
Mm-hmm. All right. Well, I definitely wishing you all the best with this project, because I think I'm not the only one thrilled about the prospect of seeing Airlanders flying around us, over us, hovering over around our cities. And actually, I'm based in Barcelona, which is not far from Air Nostrum's base. So
absolutely.
So I'm really looking.
So you have a great opportunity.
Yeah, really looking forward to seeing one of those. When is it 2027 that you are expecting it to go into service?
We're expecting to go into service in 2026.
26. Okay.
And we'll have our full production capacity coming online from 2027.
Mm-hmm. Excellent. Well, we'll be looking forward to that date then. In the meantime, where can we find out more about the Airlander?
The best place to find out more is online. Our website's at www.hybridairvehicles.com, or you can get to it through airlander.co.uk.
Excellent. Well, thank you so much, Tom, for this very insightful chat today. As I said, I repeat again, totally thrilled by the prospect of, I know it's not the right word, but the airship comeback.
It's a great story to you. And
how you call it? Actually, if it's not technically an airship, you would say a hybrid vehicle?
Hybrid aircraft or hybrid air vehicle, yeah.
Okay, so very thrilled by the prospect of seeing hybrid air vehicles as part of the transportation mix soon. Thanks you very much. Thank you. Before you go, and if you like this podcast, a quick reminder that it would be absolutely great if you could please give it a rating on Apple, Spotify, or whichever platform you're using, or recommend it to a friend or whomever might be interested. Thank you very much and see you soon.